In this video, we're going to be discussing Objective 3.2, Properties of Solids. Our topic is to explain the relationship among the macroscopic properties of a substance, the particulate level structure of the substance, and the interaction between these particles. And our skill is model analysis. So our key point is that many properties of liquids and solids are determined by the strengths and types of intermolecular forces present. We're going to specifically be talking about vapor pressure and boiling point, and melting point is kind of related to intermolecular forces, and we'll get into that as well. So vapor pressure is the pressure exerted by a vapor when the gas and liquid of a substance are in equilibrium. So here we have a cup of water, and the cup of water is at room temperature, and it's in the sealed container. So some of the water is constantly evaporating, and then some of the water is condensing back. So once evaporation and condensation are happening at the same rate, then the pressure outside of this cup of water is the vapor pressure. So because there's going to be some water molecules that have evaporated that are in the gaseous phase, some in the liquid phase, and they're constantly condensing and evaporating at room temperature. Once the rate of condensation and the rate of evaporation are equal, this pressure outside of the liquid won't be changing, and that's the vapor pressure. So in this diagram, you can see that we have vaporization, where these liquid particles are just the ones on the surface are evaporating. And then there are some that are condensing as well, but here we have our vaporization rate is larger than the condensation rate. So more of these particles are becoming vapor than are condensing. And then at our vapor pressure, we have an equal rate of vaporization and condensation. So a measure of the pressure of these molecules, of these gaseous molecules, would be the vapor pressure. The boiling point is the temperature at which the vapor pressure of a liquid is equal to the pressure of the atmosphere of the liquid. So here we have the pressure of the atmosphere pushing against the liquid. So even though these surface particles are able to vaporize, the particles in the liquid are not able to become a gas. But when we add heat, we're adding energy to these particles, and now these particles, within the liquid, can become gas. So when you see bubbles forming, when you boil a liquid, for instance, if you boil water, the bubbles are actually water vapor, the water particles spreading apart. So with both of these substances, the intermolecular forces need to be overcome. So these intermolecular forces in this liquid, the forces of attraction between all of these molecules, when they break at the surface, then the liquid becomes a gas. And so when these water molecules, the intermolecular attraction in between these intermolecular force in between all of these molecules, holding them in their liquid form. And once we break this attraction, then the water molecule can escape that liquid and is now a gas. It's more independent. It's separated from the other water molecules. So here you see boiling points of many different substances. So notice water boils at 100 degrees Celsius, whereas H2S boils at about negative 70 degrees. When you look at the periodic table, sulfur is just directly below oxygen. So this has these have the same structure. They're both bent molecules. H2S has a larger molar mass, but because H2O has hydrogen bonding, it has stronger intermolecular forces, and therefore it takes more energy to pull those water molecules apart and change it from a liquid to a gas. So water has a higher boiling point, whereas when we compare H2S and H2SE, the only difference is that SE is in period 4, whereas sulfur is in period 3. So H2SE has a higher molar mass, which means it's more polarizable, so it has stronger London dispersion forces. So even though both of these molecules have dipole-dipole forces and London dispersion forces, because H2S is a larger molecule, it has stronger London dispersion forces, and so its intermolecular forces are stronger, and therefore it has a higher boiling point. And you see the same thing with this. HF has hydrogen bonding, so it has the strongest type of intermolecular forces between HF, HCl, HBr, and HI. But notice HF is lower, has a lower boiling point than H2O, because H2O is a larger molecule, so it's more polarizable. So it has stronger intermolecular forces. Check for understanding. Compared to the equilibrium vapor pressure of CH3OH at 300 Kelvin, the equilibrium vapor pressure of C2H5OH at 300 Kelvin is which of the following? So there's a few hints. First, notice the boiling points. So C2H5OH has a higher boiling point, which means it takes more energy to pull apart molecules of C2H5OH of ethanol. And so ethanol is going to have a lower vapor pressure because fewer ethanol molecules will be able to be vaporized because of that stronger intermolecular force. So A and B can't be true. And then the difference is that we have an extra carbon, right? Between methanol and ethanol, ethanol just has an extra carbon. So our choices are lower because London dispersion forces among ethanol molecules are greater than those among methanol molecules. And that is true because we have an extra carbon, we have a larger molecule, it's more polarizable, and so we have stronger London dispersion forces, versus D is lower because the larger number of hydrogen bonds among the ethanol molecules. Notice this is the only area on both molecules that can form hydrogen bonds because we have an oxygen bonded to a hydrogen, so they both have the same potential for forming hydrogen bonds. Check for understanding 2. Which statement best helps to explain the observation that ammonia boils at negative 28 degrees Celsius, whereas phosphorus trihydride boils at negative 126 degrees Celsius? So looking at this, we know that the boiling point of ammonia is higher than the boiling point of phosphorus trihydride. So therefore, that means that ammonia has to have stronger intermolecular forces. It has a higher boiling point. And so we know that A can't be true because this says ammonia are weaker, and that can't be true. And D can't be true because this also says that it has weaker forces. So now we're just looking at the dispersion forces versus hydrogen bonding. PH3 is a larger molecule than NH3, so PH3 has larger dispersion forces. Phosphorus is in the third period, nitrogen's in the second period. Phosphorus has a higher molar mass and more electrons than nitrogen. However, so B can't be true because the dispersion forces are stronger in PH3, but NH3 has hydrogen bonding, and that is stronger than the dipole-dipole forces in phosphorus trihydride. Check for understanding 3. Based on the information in the table, which of the compounds has the highest boiling point and why? Okay, so all of these compounds have very similar molar masses. So the difference is that butanol has this area. Pentane is just carbons and hydrogens, and propanoic acid has this whole thing, besides the carbons and hydrogens. So we're looking at the highest boiling point, so that would mean the strongest intermolecular forces. So butanol, so all of these has London dispersion forces because London dispersion forces exist in all molecules. Butanol has a polar section of its molecule, so it has dipole-dipole interactions as well. Pentane is completely nonpolar, so it just has London dispersion forces. And propanoic acid is also polar, so it has dipole-dipole, but it also has this area, an oxygen bond to a hydrogen, so it also has hydrogen bonding. So the strongest intermolecular forces are with propanoic acid because it can form intermolecular hydrogen bonds. Melting point is the temperature at which forces between solid particles can be arranged into a liquid form. So here we have solid ice. When we are a solid substance, we can call it ice. When we melt it, we're breaking some of these intermolecular attractions, intermolecular forces, and therefore the water molecules can then move more freely, but they still have attractions in between them. There's still intermolecular attractions in them, but they can rearrange now. So solid was fixed, and now when we add some thermal energy, the liquid can now break free from that fixed position. However, intermolecular forces aren't completely broken because liquids are still very close. They're in very close proximity. So this is why intermolecular forces do definitely play a part in the difference between a solid and a liquid and melting point. The stronger intermolecular forces tends to have a higher melting point. It takes more energy to melt, but it's not as prevalent as boiling point because when we boil substances, we're completely breaking those intermolecular forces. We're not just rearranging them. Check for understanding 4. The graph shows the heating curve for methane. Which of the following best explains why more energy is required for the process occurring at 110 Kelvin than the process occurring at 90 Kelvin? So at 90 Kelvin, we have melting, the heat of fusion. This is melting. So P is a solid, R is a liquid, T is a gas. So to go from a solid to a liquid, we are melting it. And 110 is boiling. Heat of vaporization. So intermolecular attractions are completely overcome during vaporization. Intermolecular attractions in the solid phase are weaker than the liquid phase. That's not true. Solid has the strongest intermolecular attractions. Electron cloud of methane molecules are less polarizable at lower temperatures. That's incorrect. Methane always has the same amount of electrons, so it's the same equal polarizability. And vaporization involves a large increase in temperature. Notice when we are changing phase, the temperature doesn't change. It stays at 110 Kelvin.